Hey everyone, welcome to today's session. Have you ever thought about how fast energy gets transferred? Think about a race car zooming around the track. How fast is it using its fuel, really? That's power in action. In physics, we define power as the rate at which work is done or energy is transferred. It's the speed at which energy flows, whether it's from a motor to a machine or from the food you eat to the work you do. So, here's the first equation we look at: power equals work divided by time. Where power is the rate, work is the energy transferred, and time is how long it takes. Notice the relationship: the faster the work gets done, the higher the power. So, power tells us not just how much work is done, but how quickly it's done. Now, let's dive deeper and see how this works in real life. Alright, moving on. You might be wondering, what happens if the work is happening right now, at this very moment? This is where instantaneous power comes into play. Instantaneous power is given by P equals F times V, where F is the force applied to an object, and V is its velocity. So, it's like saying how much power is being transferred at this exact instant when the object is moving. For example, imagine you're pushing a sled. The faster you push it, the more power you're applying to move it. And if you apply a bigger force, you increase the power too. In another form, for rotating objects, we have P equals tau times omega, where tau is torque and omega is angular velocity. This comes in handy when you're dealing with motors or spinning objects. Power is all about how quickly things are moving or rotating, and it's something we use in so many real-world applications, from electric cars to wind turbines. Now, let's talk about units. You've heard the term watt before, right? It's the unit for power. So, when you use a light bulb, you often see it labeled with something like 100 watts. But what does that mean? 1 watt is just 1 joule of energy used per second. That's it. It's a simple concept, but it becomes really useful when we talk about things like horsepower in cars. 1 horsepower equals 746 watts. In your everyday life, when you buy a microwave, a fridge, or a fan, the power ratings tell you how fast they use energy. For example, a 100-watt bulb uses 100 joules of energy every second. Power really helps us compare how much energy different appliances consume and how efficiently they work. Let's switch gears and see how power works in mechanical systems. Power is the rate at which work is done. If you're lifting a box, the faster you lift it, the more power you're applying. This can be calculated by P equals F times V, where F is the force and V is the velocity at which you're lifting it. The harder and faster you push or pull, the more power is involved. For instance, in an elevator system, power is needed to lift the weight at a certain speed. If the elevator is going up at 2 meters per second and the force required to lift the load is 500 newtons, we use the formula P equals 500 times 2 and we get P equals 1000 watts. That means the motor is doing 1000 joules of work every second to keep that elevator moving at a steady pace. Okay, but power isn't just for mechanical systems, it's also crucial in electrical circuits. Electrical power is given by P equals V times I, where V is voltage and I is current. This formula helps us understand how electrical appliances work. For example, if you have a toaster rated at 500 watts, that means it uses 500 joules of electrical energy every second. Another interesting thing is when you're dealing with resistive materials, where power loss is given by P equals I squared times R, where R is resistance. This is why electrical devices like wires or resistors get hot. Energy is being converted into heat. And it's all about power. The quicker energy is used, the more heat is generated. And that's why we need things like fuses to prevent overheating in electrical systems. Now, let's do a quick example to make it all real. Imagine a 10 kilogram box is being lifted at a constant speed of 2 meters per second. How much power is needed? First, we calculate the force required to lift the box. We know F equals m times g, where m equals 10 kilograms and g equals 9.8 meters per second squared. So, F equals 10 times 9.8 equals 98 newtons. Now, using the formula P equals F times V, where V equals to meters per second, we get P equals 98 times 2 equals 196 watts. So, the power required to lift the box is 196 watts. Not bad for a simple example, right? This tells us how fast the energy is being used to lift the box. To wrap up, we've seen that power is all about how quickly energy is used or transferred. Whether it's lifting an object, running a motor, or driving a car, power is at the heart of it all. Remember, the formula P equals F times V ties power directly to force and velocity in mechanical systems, and P equals V times I does the same for electrical systems. Power helps us compare different devices, whether they're in your kitchen, on the road, or in the classroom. It's a concept that not only explains how machines work but also how efficiently they perform tasks. So, next time you plug in a device or see a power rating on something, remember, it's all about how fast energy is flowing. And that's power at its finest. I hope you've gained a better understanding of this fundamental concept. See you next time, where we'll dive into another exciting aspect of physics.